This video provides an overview on how to use the energy band diagram program created at Boise State University. The program that's opened currently is the default state for the program. What I'm going to focus on are several of the panels. I'll talk about this lower panel down here where my cursor is pointing. Then I'll talk about the leftmost panel and then move to the upper panel. I'll talk a little bit about File, Edit, View, Structure, Help, Tools, and then go into editing and changing some of these materials here. So what I show here, what is shown here, is an energy versus distance plot of three different materials. How do I know what type of materials are they? Well, as I hover my cursor over here, you'll notice that the bottom panel has four pieces of information. One is location, the other is material, the other is electric field, and the final one is potential, which is voltage. Electric field is megavolts in megavolts per centimeter. So as I hover over this particular material, it shows that it's titanium nitride, which is a conductor in this case. If I move my cursor over to the next material, that is silicon dioxide, shows a constant electric field as I move across, but you can see the potential is changing. The reason that the electric field is constant is because this material is considered a perfect insulator. Therefore, there's no charge within the material. So as I move across the material, charge isn't changing, so the electric field remains constant. The electric field is just if you think of Poisson's equation, it's just the derivative of voltage with respect to distance. Voltage is directly proportional to energy. The units of EV shows that proportionality. Constant is the fundamental charge of, or just the fundamental charge. And so that means that the electric field, since it's the derivative of voltage with respect to distance, the difference between voltage and distance is just electric field. So the slope here is representative of the electric field. As we move over into the silicon, into this area of this green material is silicon, as I mentioned. And you can see that there is a light line. This line is indicative of the intrinsic energy level. The black line, which is flat, is the Fermi energy of the material. And then you've got the conduction band and valence band. All right, so let's say I want to go into a specific material and say I want to know the electric field at this position. And which I can see at the bottommost panel, it says 7.6 megavolts per centimeter. Now let's say I wanted to copy that electric field so that I can use that number for, say, calculations outside the program. What I would do is click on this point, which will turn the bottom panel text and numbers from black to blue. The blue means that it's frozen, so I can move my cursor down there. I can select the number, and I can just do Control C to copy the number. I can unfreeze that panel by just hitting escape, and it will change from black to blue. And then I can, as I move my cursor, the numbers in the text are no longer frozen. Moving over to the leftmost panel, I can see that there are the three materials: titanium nitride, silicon dioxide, and silicon. The parameters given for silicon dioxide and silicon are the capacitance of the material, the voltage drop across the material. The reason that titanium nitride doesn't have this information is because it's a metal, so it doesn't hold an electric field. Therefore, there's no potential drop or capacitance across it. Moving up to the uppermost panel, what I see is voltage and temperature are the only two parameters that I can change. So if I change the voltage, say, to 3, I type in 3, press enter, and you can see that it changes. I can type in -3, hit enter, and we get a reverse in the voltage. polarity. Temperature I can change. I usually just leave it for room temperature. These other parameters are parameters relative to the structure itself, the device itself. So the flat band voltage remains the same. EOT, the effective oxide thickness, remains the same. Capacitance of the entire stack remains the same, and the threshold voltage remains the same. So these parameters are provided once given the structure of the material of the device. Certainly, I can copy these numbers, so I can do Control C. I can place it, say, in voltage and enter the flat band voltage, and notice that all the bands are flat. If I want to put the threshold voltages to say where's the Fermi energy at the interface of the silicon dioxide and silicon, there it is, showing that that's where the device essentially turns on, is when that amount of voltage is applied, the Fermi energy reaches this point in which the majority carriers are now holes. So these are the specific functions of this program. Now, let's say that I want to edit a particular material. Let's say I want to change the silicon, some of the parameters of the silicon. So I can right-click on that material, select Enter. Let's say I want to change the silicon from N-type to P-type. I can click on that. I can change the dopant concentration from 10 to the 18th to whatever I want. Let's say 10 to the 15th. I click OK, and you can see it changes to P-type, and automatically the program knows that if you're changing to P-type, the dopants are acceptors. And so you don't have to change the sign of the dopant concentration. If I want to change a particular material, let's say I want to change titanium nitride to gold, I can right-click, select Replace Layer, go through this list of conductors, select gold. There's several that you can choose from. I hit select Replace, and it changes. I can do the same with replacing the layer of silicon dioxide. I can, whoops, this is the wrong material. Let me make sure that I'm over the silicon dioxide, edit layer. Okay, that is silicon dioxide. Let's do replace. There we go. Here are the insulators. If I wanted to change to, say, hafnium oxide, I can select Replace. What the Replace does is allows one to just change the material without having to worry about the thickness of the material. And that's a feature that many people had wanted, so we implemented that. All right, now let's, you may have asked, well, you skipped this blue button. What is that blue button? That provides the movie mode. That means that I can do a voltage sweep. If I press it, I do a voltage sweep. And you might ask, well, I'm doing a voltage sweep from what voltage to what voltage? In order to determine that, I'd have to go under View, Parameters, and see that I'm going from -2 to 2 volts. If I wanted to go from -12 to 12, I can certainly do that. It provides the opportunity to change the number of steps if I wanted to. That's fine. Just do that. I can select it, and the y-axis changes to incorporate or allow one to see the full voltage sweep, the entire band gap. Alright, so going back to 2 volts, here I am. Now, let's say this is energy versus distance. If I wanted to view, say, the potential versus distance, I can do that by going to View and selecting Potential. I can also select Electric Field. I can select Charge Density, and it gives me these plots. Let me go back to the energy band diagram. Now let's say I wanted to change the entire structure. I can do that by changing each material, or I can go into Structure and select Compose Structure. Similarly, I can do a right click and go to to compose structure. So this provides the entire structure in each of the material databases. So I have metals or conductors, dielectrics or non-conductors, and then semiconductors. Let's say I wanted to make a MIM diode, so metal insulator metal structure. I could just delete the silicon, select, say, gold, if I wanted a gold. Ask me what thickness I want, say 5 nanometers. Perhaps I should do this particular one, 5 nanometers. And if I want to change the hafnium oxide to, say, dysprosium oxide, so I delete the hafnium oxide, select, I can select dysprosium oxide, select this one, add material, ask me what thickness, say 4 nanometers, select OK, move it up this structure, so now I have gold, or I have a metal insulator metal. I'm done, and there I am. So these are some of the things that you can do. Let's say I wanted to export the data, the band diagram, and what data am I allowed to export? Let's just do it that way. If I select that export tool, I do preview. It then calculates the capacitance of the stack, the capacitance of the oxide. So note that both of these are the same. If I had a semiconductor in there that was doped, it certainly wouldn't be the same. So potentials, electric fields, capacitances, tunnel distance, and so on. So these provide capacitance versus voltage. These are all voltage. Note that there are no distances in here. Okay, so none of the band diagrams are in here. Now how would I go about extracting those parameters? So what I can do is right click, go to chart options, and I can copy this diagram, and I can go paste that diagram elsewhere. So that's one way. The other is to export visible graph. So that allows me to create a comma separated value file that exports all the data in the energy versus distance. Now let's say that I wanted to export the electric field data versus distance. Then I would go to View, select the electric field, and go to File, and export the visible graph. And that would then export it in a comma separated value file. Okay, so that I think covers most of what the energy band diagram program can do, and that concludes this video.